Welcome back, guys. This video will discuss about acceptance sampling under unit number 5 of metrology and quality control. Yeah. So I think this could be the last video for fifth unit. So what we have seen previously, control charts and attribute charts, variable charts, how to solve with some numericals for X bar, R chart and P chart, and just for formulas for U chart, C chart, and all. Okay. Examples also we discussed for X bar R and P chart. So kindly go through textbook for more problems and try to solve it so that you will get practice. In this video, we'll be discussing about acceptance sampling. So what is acceptance sampling? Acceptance sampling is the process of evaluating a portion of the product or material in a lot for the purpose of accepting or rejecting the lot as either conforming or not conforming to quality specification. Okay, so you will be taking some portion of sample from a lot. Okay, so you can't inspect 100% inspection. You won't be doing mostly. Yeah, we can do, but it it involves cost more, time involved. So you have to allocate labor, inspector, instruments also needed. So additional totally time means cost involved, so it will add more on your unit cost. Because if you are 100% inspection you are doing, means the unit cost also will be increased, because simultaneously that inspection cost all will be added with your product price only, so customer will be getting with a higher price. So it is not advisable to do 100% inspection, all product inspection, until otherwise that particular product possesses 100% inspection. But mass production, mostly they won't go with 100% of inspection, they will go sampling. So in that sampling, what is meant by acceptance sampling? Acceptance sampling is the process of evaluating a portion. Okay, so only process of evaluating portion. So how we are evaluating the particular portion which we are taking out from the lab. Okay, so whether it is accepted or rejected. Okay, in order to confirm whether the selected samples are under the control or out of control, so that if out of control we can uh, consider about whether to reject the whole lot or we need to do for recheck or rework, like that we can. So the process to check the sampling, the process to check the sample for acceptance is called as acceptance sampling. The input or output articles are available in lots or batches. Yes, sample we are taking from the population, so sample represents the population. It is practically impossible to check each and every article of a batch, so we randomly select a few articles, that is called sample, from a batch, inspect them, and then draw conclusion whether the batch is acceptable or not. This is called acceptance sampling. Okay, this is the process, and by doing which we can decide whether a lot can be accepted or rejected. So this is the called acceptance sampling. Sometimes either way is possible. Sometimes the articles inspected are merely classified as a defective or non-defective. Then we deal with acceptance sampling of attributes. Okay. So defective or non-defective, in the sense, it comes under attributes only. Sometimes the property of the articles inspected is actually measured. Then we deal with the acceptance of sampling of variables. Like a dimensions we are measuring, like a thickness, diameter, length, like that, mass kind of variables we are measuring, then it's acceptance sampling of variables. And if we are counting the defects or defectives, non-defectives, like that, yes or no, pass or fail, like that, if you are analyzing from the sample, then it is called acceptance sampling of attributes. In terms of acceptance sampling, so when we can go with acceptance sampling, let us take some simple example as given here. Size n randomly from a batch. If the number of defective articles in the sample is not greater than the certain number of C, if we are setting some threshold value, if the number of defective articles in the sample is not greater than within the control, then the batch is accepted. Otherwise, it is rejected, right? If we are setting some threshold value or above which from the lot, if you are taking some sample, for example, 100 sample out of 100 sample, if defective items are more than 5, we have to reject. Less than 5, we can accept. Like that, we are setting. That one only we discussed about in control chart, how to set the upper control limit, lower control limit, or central limit. So based on that, we can able to fix the thresholding threshold value. Then when we are doing the acceptance sampling, if above or below, if above reject, below means we can accept. This is how we can. So this is how we define the acceptance plan. So when we go for acceptance sampling, in the sense when a particular component or product or assemblies, whatever may be the product, must be processed in a short amount of time. If you have a large number of components manufactured comes under mass production, you can't able to spend lots of time. If you don't have time to spend each and every component, and also you don't have facilities or you don't have money to or infrastructure to test or each and every component, then you have to go with the acceptance sampling plan. And also, if a component or product need destructive testing, means you have to do like a crash test kind of example it is given in this animation. There's a crash test, vehicle crash test they will be doing. So crash test they can't able to do for each and every car or automobile which is produced from the industry, automobile industry. It is not feasible. So what they do, they randomly take one, then they do that under destructive testing. Just for automobile example, I'm telling. Some other component also, they won't test each and every component with the destructive testing. For example, if compressive strength, if they want to test each and every product, they won't check compressive strength. Okay. So when during this kind of situation arise, then you have to go with the acceptance sampling. So under acceptance sampling, you will be having lots of definitions or small concepts. So I have given like a 1, 2, 3, 4, 5, 6 like that, just to go through one by one. Let us check about one by one. So acceptance quality level. So from the word itself, we could be able to understand what is this word means. So acceptance quality level. Acceptance quality level. What is this acceptance quality level? If a lot has small fraction defective, okay, it has a small fraction defective, we do not wish to reject and consider as a good lot. Yes, only small amount of fraction of defective is there, then we don't want to reject the lot and we want to consider as a good and accept. Let small p1 denotes a lot of quality, okay, quality of lot for small fraction of defective. So PR rejecting means 0.05. This implies that, so we are setting a threshold of 0.05 fraction. If, for example, 5 percentage of product from the lot is from the sample is defective, up to which we can consider the rejection ratio is up to 5 percentage. If 5 percentage is the rejection setting, in the sense we can say that 95 percentage is acceptance. Okay, accepted quality or accepted sample from the batch. So this is how acceptance quality level. So acceptance quality level either 5 or 4, 3, 2, 1 depends on the company or it depends on the quality curve we can able to set. So if acceptance rate is 95, in the sense rejection rate is 5%, vice versa. 97 means 3% is rejection rate. Okay. So here P1 is known as the acceptance quality. P1 is the acceptance quality, and the quality of this lot is satisfactory by the consumers. Second one, lot tolerance percent defective, LTBPD, or rejecting quality level. Okay. The consumer is not willing to accept the lot having proportion defective P1 greater. So if you are setting a parameters or proportion of rejection is 0.05 or 5 percentage, above which you are getting the defective percentage, then you are not ready to accept. So that lot tolerance percent defective, in the sense, what is the rejecting quality level? The acceptance quality level is 95, rejecting quality level is the 5 percentage. So above 5 percentage, if you are getting after inspection, then you have to reject. So that is called rejecting quality level or lot tolerance percent defective. So how much percentage of defective can be available in the lot or sample which you are taking. So either acceptance quality level means how much percentage or proportion you are accepting, rejecting quality level or lot tolerance percent defective, in the sense how much you are, what to say, accepting them. Okay, so this is how you have to define. Then this can be calculated by 100 into P1 is called the lot tolerance percent defective. Okay, so the P1 either 5 percentage, 4 percentage, 3 percentage, something like that, we can say. This is the quality level in which consumer regards as rejectable, and it is usually named as rejecting quality level. Okay, this quality level in which consumer regards as rejectable, and it is usually named as a rejecting quality level. That's what it is given. So that two concepts, one is acceptance quality level, another one is the rejecting quality level. For rejecting quality level, you have another term called the lot tolerance percent defective. Okay, the lot quality P1 is to be accepted at some at arbitrary and a small fraction of time, usually 10 percentage. Some time they will be keeping 10 percentage. Okay. So in order to explain this acceptance quality level and rejecting quality level, or LTBD, the quality curve drawn here, this is the quality curve, QC curve. Generally people used to say QC curve or quality curve. So in x-axis, they're given like a proportion non-conforming, and y-axis they are telling probability of acceptance. So this x and y is given in this way: proportion of non-conforming and vertical probability of acceptance. Okay, so if you have a probability of acceptance is 1, means 100 percentage acceptance started here, then proportion of non-conforming definitely will be 0. But it is not the case. You can able to get a probability of acceptance 100 percentage for most of the mass productions in manufacturing sectors. So you will be giving some allowances due to assignable causes or common causes and all. You will be giving because it is not possible to achieve 100 percentage always. You know the reasons. So what they do, they will be giving some allowances. So this is the curve, and this curve goes in this way. So once up to here, like for example 0.04 they done, means this is called your acceptance quality level. Okay, so below which you are getting quality level, this is like a rejection portion, if you consider rejection portion. So all others are accepted and only rejection portion, then you can say that it is very good and we can accept, and we can accept the lot and we can send to the next level. If it's not under your level acceptance quality level, but up to 0.08, okay, but not good condition or not great, we can say. But behind which, behind certain point, if you are telling that is very bad, we can't able to accept. Okay, so really good, okay, but not great, really bad, like that we can classify. In the sense, above 0.08 means 8 percentage rejection rate, but in this slide it is told 10. Here they are telling quality curve in generally 8. So depends on the industry they will change, but depends on the product also. So in this diagram, as per this diagram, 8 percentage in the sense, 92 percentage can be accepted, 92 percentage of acceptance quality level, and 8 percentage of rejection. So up to you have 8 percentage for error possibilities. Okay, so this one you have to consider. So mainly achieving acceptance quality levels up to here, for example, if it is 2 percentage, achieving that is not at all easy task, because you have to focus on your process, production process, or your machines and its quality, or operator who is doing machining, and inspectors, what kind of instruments you are using for inspection, various factors involved in quality, right, affecting the quality. So you have to take care of each and every factor so that you can able to attain uh, acceptance quality level more, means rejection level is less, acceptance level more, like that. So this is very, very important. So this is the operating curve, characteristic curve, OCC curve. And operating characteristic curve is a probability curve for a sampling plan. It is a probability curve for a sampling plan that shows the probabilities of accepting lots with various lot quality levels. Okay, so percentage of defectives in that, it is giving what is mean, like that. So as I said, in your x-axis, you have lot quality percentage of defective, how much percentage of defective can be placed, and in terms of y-axis, probability of accepting lot. So started with 1, then quality curve goes like this. So if you take a horizontal and vertical line, maybe here it is coming like a 0.03, means 3 percentage. Under this sampling plan, if the lot has 3 percentage of defective, in this point lot has a 3 percentage of defective, the probability of accepting the lot is 90 percentage. Yes, if you have 3 percentage defective, accepting your lot 90 percentage, and probability of rejection will be 10 percentage. So generally, as I said, 10 percentage of allowance given for rejection, in the sense number of or percentage of defective or fraction of defective needs to be 3 percentage or 0.03 only. So you can have a 3 percentage. If you have 3 percentage of defective, then acceptance is 90 and 10. So if you want, instead of 90 percentage of acceptance, if you want 95 percentage of acceptance, if you go here, then you have to reduce your percentage of lot defectives. Okay, for example, if you want to achieve 95 percentage of acceptance, if you draw the vertical line, then it will come over here. It may be 0.2 or 0.25, means 2.5 percentage of defective only you are allowed to make, behind which if you are making, you have to reject it. Okay, so this is how. Then if the lot has a 20 percentage of defective, if you have a 20 percentage of defective, it has a small probability, that is only 5 percentage of chance for being accepted. Probability of rejecting the lot is 95 percentage. So you can't able to have a 20 percentage of defective in a lot. 20 percentage is out of 100 component, if you are making, in that 20 products are defective, in the sense you should not accept, because chances of acceptance will only 5 percentage. So people will be analyzing this, and through these curves and all, in the industry, in real industries, then they will fix the parameter, what is the acceptance level, what is the rejection level, and all. So I hope you guys understood about this operating characteristics curve, OCC curve. And under this sampling plan, what is the probability of accepting a lot that has a 5 percentage of defective? If, as I said, if you have a 3 percentage of defective or 5%, if you have a 5 percentage, if you can draw here the vertical line, if you are drawing here, maybe almost 80 percentage. Yeah, 5 percentage defective if you are allowed. So from this QC curve, you can check how much percentage of acceptance I can, if I am having setting uh, what to say, 10 percentage of defective, 5 percentage of defective, or 8 percentage, 7.5 percentage. For example, 10 percentage of defective if you are setting, it will go here, maybe you will be having at most 45 percentage of acceptance only. But in terms of 5 percentage defective, you can have the quality curve like this. So you can have up to 80, approximately 80 percentage of acceptance only. The sampling plan may not be acceptable to customer. Therefore, This sampling plan may not be accepted for meeting the customer quality level, because above 90 percentage only people or customer will accept. Okay, so they won't ready to accept that defects with 5 percentage or 20 percentage. So you have to consider what the customer demands. Okay, so this curve will be useful for that. The third one, so previously we saw two things. One is acceptance quality level, second one is the rejecting quality level. Otherwise, we can call it as a LTPD, lot tolerance, percent defective, and operating characteristics curve, OCC curve, or quality curve, we can say QC curve. Then next one is the process average fraction defective. Okay, simply we can call P bar kind of things, but process average fraction defective. For example, that details given here, in any production process, the quality of product tends to settle down to some desired level, which may be expected to be more or less the same for every day for a particular machine. So in particular machine, if you are making continuous machining, so always it will be producing same, almost like a initially, maybe once you are installing a machine and you started running and producing some component, it tend to give more. After that, some point of time it will go and always give some with some percentage of allowance it will produce. Some accuracy errors will be there or tolerance, that's why tolerance. So it will be settled down and it will give constantly same amount of accuracy or tolerance which we want. Okay, if this level could be maintained and if the process is working free from assignable causes of variation, the inspection could often be dispensed with. Okay, for example, if machine got settled, you will be checking like continuously, you are checking every day, then after every 2 days, after 3 days, or every week you are checking, and always it is constantly giving same amount of defective items. Acceptance rate also same, like 95 percentage of acceptance or 90 percentage of acceptance constantly. In the sense, we can know that instead of taking sample every day, maybe we can increase the taking sample from the machine like a weekly once, like that. And instead of, so people will be saying, okay, in this particular production process or production line, these machines are there, this particular machine is constantly giving this much percentage of accuracy, or in that percentage of rejection rate is this. So what they do, they will be accepting without going for any inspection regularly, they will be accepting. But in practice, as a result of failure of machine and laziness workers, the quality of product may suddenly decrease. Okay, suddenly decrease. The process average of any manufactured product is obtained by computing the percentage of defective in the product over a long time, and it is denoted by P bar. So if process average of any manufactured product is obtained by computing the percentage of defectives in the product over a long time, and it is, for example, the percentage of defective you are expecting or predicted from the machine regularly, and you are representing that is called P bar, that is process average fraction defective. So any manufacturing production will be having multiple process lines. Okay, maybe one is doing for example multiple assembly, like a bearing assembly or other PCB board printing, or other components like what to say, some gear transmission system assembly, like that. In the sense, each and every assembly will be having multiple number of parts, individual parts. So each will go under separate production line. For example, transmission system will be having multiple gears. In the sense, each gear will go because each gear will be having different number of diameter of gear, diameter or thickness of the gear or shape of the gear, maybe different, and the rod will be there, shaft will be there, some washers will be there. Okay, some keyholes needs to be made. So each and everything will go under separate production line. So if you have process line, in particular process line, various machines like a turning operation may be there, slotting operation will be there, gear hobbing process will be there, finishing operation will be there, right? Or keyhole means you will be doing some threading, you need thread cutting also needed. So many operations involved in each and every component in the sense. It will go in particular production line where each machine will be assembled. So in that process, at the end of the process, if you are inspecting, then you will be able to know, you will be able to see that this is the average of defective items coming from this process line, like a process line A, B, C, D, like that. If you have in this process line A, you will be having 95 percentage of acceptance, 5 percentage of defective items. In B, 3 percentage, 2 percentage, again 4 percentage, like that. If you are getting, this is not for one time. Constantly you are checking that. Once you constantly checking in a repetitive manner, it is getting like a 5 percentage, 4 percentage, 3 percentage, 2 percentage, like that. Constantly you are getting same value from each process line. Then that one you can set it as a some threshold value as a p bar. Then no need to check each and every time the quality. Randomly you have to check on some certain point. Like every day you have to check. Then continuously for a month or two you are checking every day, and now you can able to set the value like a p bar. The process average fraction defective for process line A is 95, for B 97, C 98, and for D 96 again, like that. You set after 2 months of running every day you check. Then you no need to check for every day, for because cost involved for checking sampling, acceptance sampling analysis. If you want to do, cost involved, money involved. So after setting this process average fraction defective, no need to check for third month. Randomly after 2 weeks you can check again. If what we set for process line A 95, if we are getting the same, then fine. Similarly, we can check for other B, C, D. If you do, it is time saving, cost saving. So in order to set that, you need to monitor continuously and set that value. What we are setting is called the process average fraction defective. I hope you guys understood that. Then producer producer's risk and consumer's risk. Two concepts are there. So which one is consumer risk? Which one is the producer risk? So here from the graph also QC OCC curve, we can able to explain operating characteristics curve. We can explain. So terms explained here is the producer means a production or a company. The producer has to face the situation that some good lots will be rejected. The producer might demand sufficient production against such a continuous happening frequently, just as the consumer can claim reasonable production against accepting too many bad lots. The probability of rejecting a lot with 100 P bar. P bar, you know what is P bar? Previously, we calculated process average fraction defective. 100 P bar as the process average percent defective is called producer risk. This probability is denoted by alpha, producer risk. Alpha equal to capital P, P. Here, capital P is a rejecting lot of quality P bar. This is also known as type 1 error. So, how to understand that? From this diagram, we can able to understand. So, here is your OCC curve, operating characteristics curve. In that, x-axis is percentage of defective and y-axis is probability of accepting a lot. So if this is acceptance level, you are setting 3 percentage. If you are setting 3 percentage or 3.5%, whatever maybe, if you are setting here, then it is touching your OCC curve in this line. Then if you go here, maybe around 85 percentage of acceptance. So this 85 percentage, in the sense, this is called as a rejection. So this is producer risk. Probability acceptance lot is rejected in this range, because you are not accepting 100, you are rejecting this. So this is your loss for the producer. Okay, this is the loss for the producer. But in terms of consumer risk, in terms of consumer risk, if you are setting like a LTPD, rejection quality level, you are setting the rejection quality level here, like a percentage of defect you are keeping like a 15 percentage, and if you are setting in this 15 percentage LTPD, you are setting here, then your probability of acceptance will be only almost 18 percentage. Consumer, this value is the consumer risk, means probability of unacceptable is accepted, like a 18 percentage means this is overall got rejected, but consumer needs to accept this in the sense already it is not acceptable, but consumer are forced to accept this one. So probability of unacceptable is accepted if you have this value. Okay, so it should be based on the rejection quality level. So consumer risk can be plotted with the consumer like a rejection quality level. Producer risk can be understandable by the OCC curve with the acceptance quality level. So acceptance quality level, it should be like 3 percentage, 5 percentage, like that. Rejection quality level in the sense 10 percentage, 15 percentage. If you fix that percentage, 10 percentage, fixing 15 percentage for rejection quality level, that means percentage of defective 10 or 15. If it is 10 in the sense, you will be able to get here. So 45 to 50 percentage. So this area is the consumer risk. If you are setting your lot quality percentage of defective as a 10, then curve will be stop here 10 here, in the sense this is consumer's risk, means probability of unacceptable is accepted. So this is how is whether we are how much you are setting, and it's vice versa, whether customers are accepting that. So up to here, if you are setting this parameter as an unacceptable lot, here it is considered as acceptable lot. That is the meaning. If 15 percentage you are setting 15 percentage is acceptable, after which unacceptable if the percentage of defect is more than 15%, unacceptable if you are telling. But what does it mean? All this area is acceptable. All this area acceptable with respect to OCC, in the sense only in really almost 18 percentage only acceptable out of 100. But consumers are forced to accept this unacceptable batch. So this is what risk for the consumer, and also here risk for the producer. Okay, so you should understand what is the difference between producer risk and consumer risk. And rectifying inspection plans. So under that rectifying inspection plan, you have two concepts, AOQ or ATI. So we'll go in detail about this. What is rectifying inspection plan? The inspection of the rejected lots and replacing the defective pieces by standard piece. Inspection of rejected lots and replacing the defective pieces by standard piece. In the sense, once you are inspecting, maybe in P chart, C chart, or NP chart, expert chart, and all, we have alternative method, like any one particular batch or sample goes out of control, we remove that, and without that data we recalculate X bar and R, right? X bar, R, P and all we calculated and analyzed further. So instead of removing that, what you have to do, you have to take different samples, or you have to remove those product which you checked comes under defective or out of dimensions, remove that and replace with the standard product. Okay, this process eliminates the number of defective in the lot and hence improve the quality of the product. So this one you have to understand. So once you are checking a random sample, for example subgroup size is 20, in each subgroup you are taking 6 sample, and after checking each subgroup 6 sample, only like a 12th subgroup you are getting unacceptable quality, in the sense that particular 12th subgroup, what all the sample you took, like a 6 sample you took, you replace the 6 sample with the new one and check it again, it's acceptable. Okay, so if you do in that way, the process will be eliminating the number of defectives in the lot and hence to improve the quality of the product. We can able to improve the quality of the product. So in order to calculate that control chart, we removed and recalculated. But here it's a rectification process. Okay, instruction plan. These plans are called rectification inspection plan, and it was first introduced by these guys during World War. Okay, so why in the sense mostly this guy simply they are rejecting the batch during that period, particularly this period, World War time. It's no meaning because they involved lots of money, labor, time. So instead of rejecting, what they done, they replaced the sample alone, which they took from the subgroup with the standard one, and they accepted that. Chances of risk also there, but they don't want to reject subgroups, so they replace. These plans enable the manufacturer to have an idea about the average quality of the product. The rectification process is performed in different stages of production through the combination of production, sampling, inspection, rectification of the rejected lots. So, rectification process will involve various stages performed in different stages of production. Either each and every process end they will be doing quality check and replace. Okay, or sampling inspection they do. In that sampling inspection also they do rectification plan, or after rejection also they can do the rectification process. Most of the rectification inspection plan for lot by lot sampling called 100% inspection of the rejected lots and replacing the defective pieces. Okay, so in this rectification inspection plan, you will be taking lots of sample and check it. If it is rejected, replace with the standard one and accept that. Again, you are checking some other subgroup, take some sample and check it. If the samples are rejected, then replace and do. So mostly you will be accepting 100%. Okay, so this inspection plan proposes for accepting 100%. Okay, the two important quality control concepts related to rectifying control concepts related to rectifying inspection plan under this plan are average outgoing quality and average total inspection. So average outgoing quality needs to be what? They want incoming quality level. Maybe obviously we can understand from this rectification plan, inspection plan, is incoming quality level means after product being manufactured, it is coming to the inspection center. In that, maybe 2%, maybe 3%, maybe 4% of rejection possible. But under this rectification inspection plan, what you are doing, that what all the percentage of rejection you are replacing with the standard one. So acceptance rate will be 100 only. So average quality, so outgoing quality of acceptance will be 100 only. So average quality of product after sampling and 100% of inspection of rejected lots is called average quality of product. So average quality of product after sampling and 100% of inspection of rejected lots is called AOQ. What is AOQ? Average outgoing quality. The average amount of inspection required for the rectification inspection plan is called ATI. Okay. How many number of inspection you are going to do? That average under this particular rectification inspection plan is called ATI. ATI is mean average total inspection. AOQ in the sense average outgoing quality. So, two concepts involved in AOQ. What is that? First, you do the sampling, sampling plan or sampling analysis or acceptance sampling you will be doing. After doing acceptance sampling with what? With your producer risk or acceptance level, acceptance quality level, you do that. Then you will be classifying this is accepted, this is rejected. For example, 90% accepted, 10% is rejected. Otherwise, 3% of defective, 97% of non-defective, like that. So in that 3% of defective is there after your acceptance sampling. What you do, that particular 3% maybe some numbers will be there. Replace that and do replace with the standard component, and again you do inspection, then you will be accepting that. So that is 100% inspection of rejected lots So this combination, two combination is called average outgoing quality. So average outgoing quality mostly 100. And how many number of inspection you are doing for the rectification inspection plan. For example, as I said, acceptance sampling you are doing 3% are defective in the sense if 3% are defective is how many number in terms of value number of product or amount you are discussing, that is called your average total inspection ATI. Okay, average outgoing quality limit. What we saw here is average outgoing quality AOQ, but AOQL, average outgoing quality level. What does it mean? Sometimes the consumer is guaranteed a certain quality level after inspection, regardless of what quality level is being maintained by the producer. Let the producer's fraction defective, that is lot quality before inspection is P. This is termed as incoming quality. Yes. The fraction defective of the lot after inspection is known as outgoing quality. Yes, after your inspection, if it is going to the consumer, it's a outgoing quality of the lot. The expected fraction defective remaining in the lot after the application of the sampling inspection plan is termed as average outgoing quality, P bar. Yes, obviously it is function of the incoming quality. Yes, based on the incoming quality, you are doing sampling acceptance sampling plans, and you are giving that output. That is your average output quality. But you need a limit for what to say average outgoing quality level. In the sense, you have some of the problem, so some of the equation or relationships are there. For rectifying inspection, a single sampling plan calling for 100% inspection of the rejected lots, the AOQ values are given by the formula. Okay, for rectification inspection, single sampling calling for 100% of inspection of the rejected lot. As I said, 3% are defective in the sense how many number of product is there under 3% of defective, you take and inspect all. That is what your rectification inspection plan. The average outgoing quality values are given by this formula is, that is P kind of bar. If you are considering AOQ equal to P bracket capital N minus N, and in whole bracket PA by N. So here N is a lot size, N is the sample size, PA is the probability of acceptance of the lot. Okay, so what is P is, it is function of incoming quality. So the relationship with respect to lot size, sample size, and probability of acceptance of the lot, and incoming quality level, if you make, then you can able to get the average outgoing quality level. Okay, so this one we can able to get. So this is the relationship for average quality level, where you have to consider incoming quality small p, and capital N lot size, small n sample size, and probability of acceptance PA, probability of acceptance of the lot. So with this we can able to get the average outgoing limit. So directly we can get like this. If n is small compared with n, then a good approximation of the outgoing quality is given by. So how we can able to get the, if n is smaller than n, in the sense P into PA. So P is what? Incoming quality level. Small p is what? Incoming quality level. Capital PA is what? The probability of acceptance. So probability of acceptance is what? This one. So if you have that, we can get direct relationship. If the defective pieces found are not repaired or replaced, okay, if you are checking acceptance sampling and you are getting some rejection, you are not doing any rectification inspection plan, means what? It is not repaired or replaced, then the formula must be modified. If you are not doing any replacement or rectification, formula needs to be modified. So what is the formula for AOQ? average quality level limit, average outgoing quality level AOQL, in the sense P in bracket n minus n into PA divided by this one. So if we rewritten in this format, we can able to get. This formula is not generally used, and if P is small, there is not much difference between question 2 and 3. So if P is not small, no, if P is small, we have to use. If you are not replacing, only you have to go and identify this method. Okay, if your P is small and you are replacing, then better to go with this equation. So this is what your average outgoing quality limit. In general, if the P is incoming quality and a rectification inspection plan calling for 100% inspection of the rejected lot is used, then AOQ. So this is what people will be looking forward. They are not going to take this one because they inspect and simply they don't want to reject. So mostly the equation number 3 mostly not preferred by the industry, or formula or this relationship not preferred by the industry, because they are not considering for the replacement or rectification instruction plan. But after doing acceptance sampling, here they are doing acceptance sampling and they are identifying percentage of defective, and they are ready to do the rectification inspection plan and replacing and doing 100 percentage of inspection of the rejected lot. Then the average quality limit will be, you have the relationship like this: P PA in bracket P. So P is incoming quality level, PA is acceptance probability of acceptance in bracket again P. So through this relationship you can able to get the acceptance quality level, acceptance outgoing quality limit. Okay, so you should remember this one after doing 100 percentage of inspection, sorry, after doing acceptance sampling and the rectification inspection plan, what is your average outgoing quality level? Small p into PA divided into P. This one. Before that, if you have n number, is the P into PA. Okay, so here there is a possibility of rejection rates are there, but here rejection rate is not there. So you do 100 percentage inspection through your rectification inspection plan. Okay, so this is your relationship for your average outgoing quality limit. Okay, so how you are setting the incoming quality level, how this incoming quality level and the acceptance outgoing quality varies. Okay, so if your incoming quality level is low, then you will be keeping acceptance outgoing quality level also low. At certain point, you will be achieving incoming quality level better and acceptance outgoing level also better. So this is how the average outgoing quality curve goes. Then sampling plan, in the sense you will be having different sampling plan. Is that an outline for the measurement to be taken, when we done the measurement, for what and by whom, like that we'll be having, and how we are choosing that sample, or how we are choosing the population, what is the sample size, what is the sampling procedure. In that category, we have to follow certain number of procedures for sampling plan. First, we have to identify the parameters to be measured. What kind of parameter we want to measure, we have to identify. Then range of possible values we have to set, and the required resolution we have to set. Then we have to design a sampling scheme that details how and when samples will be taken, either every 1 hour or alternate 1 hours, or forenoon session, afternoon session. Like if you have 8 hour cycle, every 1 hour or every 2 hour or every 3 hour or every 4 hours, like that, or weekly once, like that you have to. So you have to design sampling scheme that details how and when samples will be taken. Then select the sample size. We have to properly select the sample size. Then how we are going to store the data, how we are analyzing the data, what kind of inspection plan, whether we are going for rectification inspection plan, we have to check. So based on the sampling plan, acceptance or rejection or rectification, you have acceptance or rejection in the sense based on number of samples, single sampling, double sample, multiple or sequential. Like 4 different methods are there for acceptance or rejection. Rectification is totally different. So by doing the acceptance sampling, if you are going for a rectification inspection plan, it is different process. But if you are not going for rectification inspection plan, you will be going for either acceptance or rejection. If we are going for acceptance rejection, you will be having different type of sampling plan: single sampling plan, double sampling plan, multiple, or sequential. So in terms of single sampling plan, under this plan, your lot is accepted or rejected on the basis of a single sample drawn from their lot. You'll be taking a sample once, and you will be setting some acceptance level, upper control limit or lower control limit. You'll be inspecting through instruments. You will make a decision whether accept or reject. That's it. So in that, what is the process? Draw a single sample of size n, that is n component of parts. The sample size may either be calculated or found from the table. Yes, how to set this n? By experience in the industry, they will be setting some values out of this batch, like 1,000 component. We have to take 10 percentage or 5 percentage, like that. They will be setting, or some statistical table or factor table is there. From that, they can able to set that sample size. They take and inspect and find whether it's accepted or rejected. So once they take n, inspect the sample and find the number of defective components d. If the defective pieces are exit the acceptance number, if you are setting the acceptance number as c, behind which if you are getting the number of defective components, like a d, small d is greater than capital C. Capital C is what? Acceptance number. So comparing with acceptance number, defects are more, in the sense directly you are rejecting the lot, because you are rejecting the sample. By the way, you are rejecting the lot. In this case, lot is rejected. Inspect each and every pieces of the lot and replace with the defective parts, or salvage or correct the defective parts. We can do. You are not going to take second sample, third sample. What you are going to do, you will decide based on sample, reject or accept the lot. If it is rejected, what you have to do, inspect each and every pieces of the lot and replace the defective parts, or salvage and correct the defective parts. Is that good process? You are rejecting the sample which you taken out of big lot. That sample which you've taken is rejected. So if you are simply you are rejecting the lot, not going to be helpful for you. So what they are suggesting, if you are rejecting, then each and every part in that lot must be inspected and replaced. It's too much. It's too much involved, cost involved. But in this one, what are the characteristics of single sampling plan? A single sampling plan is easy to design, explain, and administrate. It is only practical type of sampling plan under conveyed production condition, when only one sample can be selected. It's also limitation. They are not preferring, if they have the constraint of selecting only one sample, in the sense they have to do. It involves lower cost of training and supervising employees, transporting, sorting. This very accurately estimate the lot quality. Okay. So single sampling means it is only restricted to take small sample, or sorry, one sample, in the sense your lot size may be small. So once your lot size is very, very small, in the sense if it is rejected, you can inspect each and every component in that lot and replace with the standard one if it is got failed. But another concept is the double sampling plan. If it is not possible to decide fate of the lot on the basis of the first sample, instead of inspecting each and every component, you have to choose second sample is drawn out of the same lot, and the decision whether to accept or reject the lot is taken on the basis of the combined result of the first and second sample. So, in the single sampling plan, what you've done, you've taken a single sample, tested, reject or accept a decision. Accept means no issues, accept a whole lot. Reject in the sense, then each and every part or component in that lot needs to be inspected and replaced with the correct one if there is a mistake, then accept everything. But in terms of double sampling plan, first you check with the single sampling plan, and in the single sampling plan itself, it's getting rejected. Instead of checking each and every component, they do second sample. They select one more sample and inspect, and with the level of first sampling rejection acceptance rate and second sampling acceptance rate, combination of that, they will be deciding whether to accept or reject the overall lot. Acceptance number in the sense comparing with C1, C2 is greater. C2 is means under double sampling plan. So this is how that overall curve will go. Inspect a sample of size N1. Count defective parts KW. If you count KW, if K1 in the sense from the single sample, if you are calculating, and if the K1, like a number of defectives, is less than your threshold, the C, you will be having some value for acceptance, right? The C value, C1 value, if it is equal or lesser than your defects, then you can accept the law. In other way, you have to go with the double sample. So double sample in the sense your K1 needs to be in between C1 and C2. It may be greater than C1 but lesser than C2. In that sense, draw another sample size means instead of N1 you will be taking N2. So total number of sample size will be N1 plus N2. Then you will be checking, inspecting total N1 and N2, and you will be checking K1 and K2. So if both K1 and K2 is less than C2, then accept the lot. If K1 and K2 total is greater than C2 value, then you can reject the lot. In another way, if C2 is greater than K1 itself, then you can reject. So this is what your double sampling plan. Multiple sampling plan is the next level. A multiple sampling plan accept or reject a lot based upon the results obtained from the several samples. It's not single or double. You will be taking several number of samples and you will be making a decision whether to accept or reject. Similar to double sampling plan, as successive trials having independent acceptance or rejection or inclusive output are conducted. Choice of method among double and multiple sampling plan depends on primarily cost and time, number of items and batch or samples. So in lot, if you have very small amount of lot, then you are going for multiple sampling is meaningless. Okay, it depends on the lot size and how many number of samples you are taking or how many number of batch you have. That also matter for going for multiple sampling plan, and also whether cost and time is reasonable or feasible for us, we can go for multiple sampling. So characteristics of multiple sampling plan. A multiple sampling plan involves smaller first samples than single or double. So in terms of single sampling plan or double sampling plan, you will be taking first sample size like a N1, if single sampling plan N, leave it not N1, N. But in terms of double sampling plan, you will be having single sampling plan second also. So N1, N2. So comparing to N1, N2 or comparing with N, the sample number is very, very small in terms of multiple sample number. For example, in N single sampling plan, you are taking 10, or in N1 10 and N2 also 10, you are taking, or 20 you are taking. But in terms of in terms of multiple sample, instead of 10, you have to take 5 samples only. Okay. So that is the characteristics for multiple sampling plan. Because number of samples which you are taking will be more in terms of multiple sampling plan. Multiple sampling plan is comparatively difficult to design and explain and expensive to administrate. Yes, so many number of samples you are taking, inspecting. So cost and expensive, then you have to administrate and maintain, manage. It involves a higher overload cost as compared to single and double sampling plan. So single and double sampling plan you can finish in a quicker way, but not possible here. You have to maintain lots of record. In theory, multiple sampling may often permit lower total inspection than double sampling for a given degrees of protection because of smaller size. Since you are taking a small number of size, it also says that lower total inspection comparing with the single or double sampling. Sequential sampling plan, also known as item by item analysis. In this plan, sample size is increased by one piece. So every sample, every time when you are doing sampling, you have to increase one sizes in your sample. So not all sample sizes are equal. For example, first sample is n. Next sample size will be n plus 1, n plus 2, n plus 3, n plus 4, like that we go. becomes large enough and contains sufficient number of defective pieces to decide intelligently whether to accept or reject. So sequential sampling plan also somewhat better. So I'll be winding up this video with this. So in this particular video, overall we discussed about acceptance sampling. What is meant by acceptance sampling? Under acceptance sampling, you will be having acceptance sampling of attributes or acceptance sampling of variables. Then why we need to do acceptance sampling, when we need to do the acceptance sampling, when you have the large number of items or lot batch, or when you need destructive testing needed for your components, then you have to go for acceptance sampling. So in terms of acceptance sampling, you need to set your acceptance level. So either acceptance quality level or rejecting quality level, like two parameters are there. Okay. And operating characteristics curve and other parameters like a process average, fraction defective, producer risk, consumer risk, rectification instruction plan. Under the rectification instruction plan, we have discussed about AOQ. AOQ means average outgoing quality, and ATI means average total inspection. And here we can able to calculate the average outgoing quality limit, AOQL. So under AOQL, you can able to get value for AOQ is P, like a P prime. Here P into capital PA, small p is incoming quality, and capital PA is the probability of acceptance. If you are not doing any repair or rework, you can consider this equation or relationship for AOQ. But mostly in industry, they will be going for rectification inspection plan. So if you are considering the rectification inspection plan, in the sense, what are the product being rejected from the law from the sample needs to be replaced, then you can able to find this relationship again, P into capital PA in bracket P. So this is the relationship for EOQ if you do rectification inspection plan. If you are not doing rectification, then with the sample size is small, you will be having this relationship. Okay. Then you have the different types of sampling plan: single, double, multiple, and sequential. Single means only you are taking one sample from that, do the inspection. If it is accepted, accept the lot. If it is rejected, each and every component in the lot needs to be inspected, and you make a call. The double sampling plan, in the sense, from the single sampling plan, if it is rejected, you have to take one more sample and check the relationship of rejection, like number of defective N1 and N2, or defective means K1 and K2. Within this range or out of range, you can check. If it is within, then accept, or otherwise reject. Multiple, in the sense, instead of taking big number of sample size, you have to take small number of samples, but multiple number of samples you have to take and inspect. Sequential, in the sense, every time when you are taking sample size, you have to add additional samples with your sample size. For example, n you are taking the first in during the first sample, next sample when you are taking n plus 1, next one n plus 2, like that. So this is how the sampling plan classification is there. So up to this, I'm winding up a recording for this particular unit number 5. So altogether, unit number 5, we discussed about control charts and acceptance sampling. So this particular unit classified into two categories, as I said in the beginning itself. So first half and second half. First half is telling about what is meant by control chart, what are the types of control chart, how we can able to prepare the control chart. But second half is telling about the quality control, PUC curve, or outgoing characteristic curve, or AQL, LTPD, or AOQL, or single sampling, multi-sampling, double sampling, sequential sampling. And at the beginning, we discussed about what is quality, how quality inspection, quality assurances means what, or what are the causes of failure, or reason for not getting the proper quality, assignable or chance cost. We discussed. So this unit is very simple. Mostly you guys relate with the industry aspect with the example. So read a textbook for because textbook will give different examples, so that understanding level will be better. So I'm winding up this video. So best wishes for you guys.